Hello, everyone. So I'm really glad to introduce today Laurent Côté. He's going to speak about actions filtrations associated to smooth categorical compactifications.
Sorry, I just technological problem here. Can everyone hear me?
Yes.
Okay. Okay, so I'd like to start by thanking the organizers for the invitation to speak today. I'll be talking about a joint project, which is partly in progress with Baris Kartal. Our original motivation was to study action filtrations on wrapped Fukaya categories. But we ended up considering purely categorical notions of action filtrations, and then we try to relate them back to their geometric cousins. Okay, let me see. Does this work? Okay. All right. Okay, so I want to start by giving some purely categorical definitions. And let me reassure you that
Laurent, the second page, the two pages are equal size. One is that. Or
is that okay? Yeah, I haven't actually given a slide talk before. So sorry. Can we just proceed like this?
Yeah, we
probably
can.
doesn't hurt.
But
okay, let's do it.
Some people is gonna be too small, but.
Okay. Let's see.
Yes, it's kind of impossible to read, I would say.
Okay. Great. Let's see. Is it any different now? Is this different?
Yeah, it's bigger now.
Oh, okay.
Yeah.
Yeah,
okay.
that's very good.
Oops. Okay. Okay. So yes. So I want us to start with some purely categorical definitions, but I'll move on to some examples as quickly as possible. So the starting point is there's a notion of what it means for an infinity category to be smooth, and I'd like to let C be such a thing. So C is going to be a smooth infinity category. And there's also a notion of what it means for an infinity category to be proper. And I'd like to let B be such a thing. And let's say that a smooth categorical compactification of C is just going to be a map from B to C. And we require that the kernel of this map is split generated by a finite collection of objects, and that the induced quotient map from B mod the kernel is a Morita equivalence onto C. And this notion appears, for instance, in recent work of Efimov. Let's see, whoops. Okay. Sorry. Okay, so smooth categorical compactifications of a fixed category C can be organized into a category. We define morphisms by requiring that a certain rather natural diagram commutes. And we say that two categorical compactifications of the same fixed category C are equivalent up to zigzag if they're connected by a zigzag of morphisms in this category of compactifications of C. Okay, so I haven't told you what a smooth and proper infinity category is. I haven't told you what a Morita equivalence is. And I obviously don't expect that everyone should be familiar with these notions. But rather than defining them precisely, I'd like to just focus on some examples because my feeling is that somehow these definitions are really abstractions of these examples. Okay, so let's begin with an example from algebraic geometry. And this is perhaps the most important example to keep in mind. So let's fix a smooth open algebraic variety U. And it's known by work of Nagata and Hironaka, I believe, that you could include U in some smooth and proper algebraic variety X, such that the complement of U inside X is a divisor. Okay, so now we apply dbco. So we pass the coherent sheaves. And this gives us a functor from dbco of x to dbco of u. And the fact, which is, I believe, due to Thomas and Troba, although I'm not entirely sure of the original attribution, is that this functor is a smooth categorical compactification. So just to emphasize this point, we have a geometric compactification of this open variety U by a variety X, and this induces a categorical compactification when you pass the coherent sheaves. There's also a uniqueness statement. So it can be shown using the weak factorization theorem for birational maps that this smooth categorical compactification is actually independent of your compactification of U up to zigzag of compactifications. And the point is just that if you compactify U in two different ways, well, these two geometric compactifications are going to differ by a sequence of blow-ups and blow-downs, and those induce morphisms of smooth categorical compactifications. So there's also a uniqueness statement. Okay. Okay, oops, let's see. So let's now move to a symplectic example, and this is probably the most important example for the purpose of this talk. So let X be a Liouville manifold. The Fukaya category of X is an infinity category, and it's an important invariant of the Liouville manifold X. And given a closed subset of the ideal boundary of X, and such a subset will be called a stop, you can also consider the partially wrapped Fukaya category, which is an invariant of the pair consisting of X and the stop. And there's a natural functor from the partially wrapped Fukaya category to the wrapped Fukaya category, which is often called stop removal. And the following fact is going to be very important in this talk, which is that if your chosen stop is a page of an open book decomposition of the ideal boundary of X, and if moreover X is Weinstein, then this stop removal functor is a smooth categorical compactification of the wrapped Fukaya category of X. So yeah, both the formulation of this fact and its proof rely on deep properties of wrapped Fukaya categories of Weinstein manifolds, which are mainly due to Ganatropart and Chende, but building on contributions from many other authors. So just to emphasize this, I mean, implicit in this, the statement is, first of all, the fact that you have such a functor, the fact that the wrapped Fukaya category of X is smooth, the fact that the wrapped Fukaya category of the pair is smooth and proper. You have to prove a lot of things, and many of these things are quite deep. Oops. Okay. So yes. According to work of Giroux, any contact manifold admits an open book with Weinstein pages. So the conclusion of this fact, or the corollary of this fact, is that the wrapped Fukaya category of X always admits a smooth categorical compactification according to the procedure on the previous slide. So you can also ask about the uniqueness of this categorical compactification. And we again have a similar statement to what we had in algebraic geometry. So let's take F1 to be a different page arising from a different open book decomposition of the ideal boundary of X. Well, it can be shown that for the purposes of studying wrapped Fukaya categories, you can actually replace these pages F0 and F1 by their cores, which are isotropic. And after perturbing the cores, you can assume that these cores are disjoint. And so you get a zigzag, as in equation number 6, of stop removal functors, which is in particular a zigzag of smooth categorical compactifications. And so we get exactly the same sort of uniqueness statement as we had in the algebraic geometric case. Okay. So unfortunately, there's an annoying technical point, which is that we don't at the moment know how to prove that the top category W of X comma C naught union C1 is proper, although we're pretty convinced it is, but in fact this doesn't actually matter for any of the applications. It's somehow enough to know that it's on a different note, I should say that there's actually no need to limit ourselves to considering stops which arise from open book decompositions. More generally, let's define a stop in the ideal boundary of a Liouville manifold to be compactifying if it deforms to a mostly Legendrian stop. So mostly Legendrian essentially means isotropic. And the Fukaya category of the pair X comma C is proper. And if X is Weinstein, it's a fortiori smooth. So it can be shown that pages of Weinstein open books give compactifying stops, but these are not the only examples. And a different example, for instance, if X is the cotangent bundle of a manifold, then you can take C to be the union of the conormals of a Whitney triangulation. And there are other examples that one can consider. Okay, so let's move on now to talking about filtered infinity categories and growth functions. Unless there are questions, should I move on?
Can I ask a couple?
Sure.
So in this example of the wrapped category, it looks like these potential compactifications almost look like they form a semi-lattice. I mean, you know, the example you gave is give these two pages and union them, for example. And you could do that with collections. So it seems like, you know, it's not so much independence up to zigzag, but the system actually forms a lattice. Is the same true in algebraic geometry? Just, you know, by specifying the exceptional divisors that you're blowing up and blowing down with respect to, can you just either union or fiber product them to also get a lattice of these things?
I'm not sure. I don't see how. I certainly don't see how.
So it's not true that these things have meets, for example.
I'm sorry.
So it's not true that the system of compactifications has meets.
What's a meet?
That there's a biggest, that for any finite collection of such compactifications, you can find a unique one that maps to each of them in a terminal fashion.
I don't see why, but I'm extremely non-expert in algebraic geometry, so this might be true for trivial reasons.
Thank you.
Sorry. Okay. Okay, so I want to move on then to talking about filtered infinity categories and their growth functions. So to begin with, a definition. So let's fix a pair of functions, f1 and f2, from the natural numbers to the real numbers. And we say that these two functions are scaling equivalent if they have the same asymptotics up to rescaling in the source. And so more precisely, you can, well, if there exists constants C1 and C2 greater than 1, such that f1 of C1 of n plus C2 is greater than f2 and vice versa. So good examples to keep in mind, two polynomials are scaling equivalent if they have the same degree, and exponential is not scaling equivalent to any polynomial. So this is essentially an equivalence relation you can impose on functions from the natural numbers to the real numbers. And we'll return to this equivalence notion. Okay, now let's talk about filtered infinity categories. So a filtered infinity category is simply an infinity category enriched over filtered complexes. So more precisely, for every pair of objects, K and L, you have a filtration on HOM of KL. And we'll assume that the filtrations in this talk are all indexed by the natural numbers, which is to say that sort of FP for P negative is just going to be 0. And we require, moreover, that the infinity operations respect the filtration. So for instance, if K equals 2, this means that the product of an element in FP with an element in FQ is inside FP plus Q. if you have a filtered chain complex, you can automatically filter the cohomology of this chain complex according to the prescription in equation 7. And this is sort of the standard thing to do. And you can check that if you have a filtered infinity category, then the cohomology category is immediately filtered simply by essentially equation 7. Okay. So, okay, so I want to define now an invariant of pairs of objects in a filtered infinity category, which is going to be called the growth function. So given a pair of objects, K and L, we're going to define the growth function to simply be the function which assigns to the natural number P the dimension of Fp in the cohomology category. And this depends on B as a filtered infinity category. So if you take the same infinity category and give it two different filtrations, there's no reason to expect the growth functions to be the same. Okay, so we now come to the main, I would say the main result of this talk, and certainly the main construction. So this construction essentially relates smooth categorical compactifications with filtered infinity categories. So let's fix a smooth categorical compactification B of a fixed smooth category C. And we'll assume, moreover, that B and C are pre-triangulated, but let's ignore this point. So what does this mean? Well, by definition of smooth categorical compactification, we can choose a finite collection of objects D1 to dk, which split generate the kernel, and such that the induced map of B mod D1 to dk to C is a Morita equivalence. So a fact which essentially follows from the construction of a quotient of infinity categories is that this quotient is actually essentially naturally a filtered infinity category. It's simply a by construction. But the filtration depends on the choice of D1 to dk. So
excuse me, Laurent, is
yes.
Filtration of finite length?
I mean, if you pick D1 to dk, yeah, then yes.
So the filtration length is in fact how many elements of the DIs are.
The filtration length is the word length.
Yeah, the word length. Okay.
Exactly. Yeah. Yeah. So it's always finite. I mean, regardless, you could also have an infinite family in the kernel, and it would stop. So the main theorem is that, in fact, the growth functions don't depend on these choices. So if you were to pick a different collection of split generators D1 to dk, you would actually get the same growth function up to scaling equivalence. And in fact, more is true. This growth function actually only depends on this smooth categorical compactification up to zigzag. So this is a sort of purely categorical statement. And the upshot of it, I guess, is that sort of if you fix your smooth category C, then the data of a categorical compactification of C up to zigzag endows the objects of C with a growth function, which is well defined up to the scaling equivalence. Okay. Oops. So this is the construction. So I guess I'd like to start now by talking about computation. So we have this sort of categorical invariant, but the question is, can you actually compute anything? Because I should say that this model of the quotient category it's rather atrocious. It's a gigantic chain complex. It's not at all obvious that you can actually understand what this filtration is. So I'd like to start by talking about that now. So before getting into the computations, I want to make a quick remark on colimits. So if you have a sequence of morphisms of vector spaces, and I believe this is often called a filter-directed system, then you can filter the colimit. And what you do is you just follow what's written in equation 11. So you take the filtration to be the image of the FP of colim is just the image of C of P. And let's refer to this as the colimit filtration. Okay. Oops. Okay. So I would like to begin by revisiting the previously discussed examples from algebraic geometry. So as before, let's take U to be an open algebraic variety. And let's take X to be a smooth compactification of U, which means that X minus U is a divisor. And recall that there's an induced map from coherent sheaves on X to coherent sheaves on U, which forms a smooth categorical compactification of dB co of U. Okay, so it can actually be shown that if you fix a pair of elements, F and G, inside dB co of U, then they actually admit an extension, which I'm calling F bar and G bar to dB co of X, such that the image of F bar and G bar under this categorical compactification is precisely F and respectively G. And moreover, you can compute harms of F and G inside dB co U as a colimit of harms of F bar and G bar tensored with this certain other sheaf, where the harms are for F bar and G bar are computed upstairs. So there's this equation 12 in the slides, which tells you how to compute the harms of FG in terms of harms upstairs. And let's let gamma of Fg upper script X be the growth function of F and G associated to this colimit filtration. And I want to emphasize that although I've written gamma of F comma G, this growth function a priori depends on my choice of categorical compactification X. It might also depend on the extensions. So it's not obvious from the notation that it only depends on F and G. But we do have the following proposition, which states that, in fact, the growth function of gamma sub Fgx agrees up to scaling with this abstract growth function, which is defined from the categorical compactification, in which we already saw in the previous slides, is well defined. So this gives a first computation. Okay. In symplectic geometry, we have a similar story. So let's take X lambda to be a Liouville manifold, and let's fix a pair of Lagrangians, K and L, which are cylindrical at infinity. So these are essentially objects in the Fukaya category of X. And it's a fact that you can actually define wrapped Floer cohomology of KL as the colimit of the ordinary Floer cohomology of KL, where you sort of apply a Hamiltonian to K. So phi sub NH is the Hamiltonian flow of n times H, where H is any Hamiltonian which is cylindrical and linear at infinity. So wrapped Floer cohomology is also a colimit. And therefore, it has a colimit filtration, or colimit growth function, and we're going to let gamma ham sub KL be the growth function coming from this colimit description of wrapped Floer cohomology. And this invariant was studied by MacLean, Frauenfeld de la Broche-Schlenk, Alves Maiweis, and many others, and it's been used for fantastic applications. And similarly, we can do essentially the same definition for symplectic cohomology, which can be written as a colimit of the Hamiltonian Floer cohomology of X with respect to a Hamiltonian function H, which is cylindrical and linear in infinity. And we also get an associated growth function, which was studied by MacLean, building on work of Seidel, and has also been used for fantastic applications.
Laurent,
yes.
we see questions in the chat.
No, sorry.
There were a few, so I can.
Okay, let's. Okay, let me. I see. Okay.
I think you.
IT is anything like a converse. Let me see. Okay, is there anything like a converse? Yes, is there anything like a converse, even very partial with the structure with filtration, yields a categorical compactification? Is there anything like a converse?
The second chat message is an attempt at a naive non-answer.
Okay. Yeah, I see. I'm afraid I don't think I have anything useful to contribute to this discussion. Yeah, but thanks for the question, and thanks also for the answer. Am I missing anything else in the chat?
It's good. It's good.
Okay. 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 Oops. Sorry, again. Okay. Okay, so I was talking about these growth functions associated to wrap Floer cohomology and to symplectic cohomology, and which come from the fact that you can present these invariants as a co-limit of ordinary Floer cohomology of a pair of Lagrangians, or ordinary Hamiltonian Floer cohomology of a manifold with respect to a cylindrical Hamiltonian. So I would like now to relate these growth functions, which I was calling gamma ham, to growth functions coming from the smooth categorical compactification. And the proposition is that if you choose a compactifying stop of your Liouville manifold, and you consider the associated smooth categorical compactification, then the growth function that you get actually agrees up to scaling equivalence with the growth function, which comes from the Hamiltonian. So somehow the invariant on the invariant gamma ham was the one which was studied by various authors previously, and which is well understood invariant in symplectic topology, and it turns out that it's the same as this purely abstract categorical growth function. So this is sort of immediately useful for computing things because thanks to work of various authors, we understand now a lot of things about the growth function for cotangent bundles. So in particular, if you take M to be a pointed manifold and you fix your favorite Riemannian metric, you can consider loops of length at most L, where L is an integer. And this includes into the space of all loops, and you get an associated filter-directed system. And you can also consider the growth function from this filter-directed system. And thanks to work of Abundadlo-Schwarz, Buzaid, and MacLean, we know that actually this growth function is the same as the one coming from Hamiltonians. And so in particular, we find that this categorical growth function is actually a purely topological thing for cotangent bundles. Okay. So actually, these two previous computations, namely the computation of the growth function for open algebraic varieties and the computation of the growth function for Weinstein manifolds, are actually at least morally special cases of a more general statement. So we take f to be a spherical functor from A to B, where A and B are two, well, actually, so sorry, let me move back. So first of all, I should say that there's a notion of a spherical functor, and the definition is not so important, but the main thing about it is that if you have a spherical functor from category A to category B, then induces what's called a spherical twist, which is an autoequivalence of B. And so you can consider the filter directed system, which comes from this spherical twist. And you can consider the growth function. And actually what we really prove is that is that the growth function associated to this spherical twist agrees with the growth function coming from the smooth categorical compactification. And so concretely in the previous examples, one of the spherical twists is something like tensoring with section of the line bundle associated to the complement of U inside X. And the other spherical twist is just wrapping ones. So it's known in particular by work of Sylvan that this is indeed a spherical twist, but we don't actually prove the theorem quite that way, mostly for technical reasons. Okay. Okay.
Laurent,
yes.
can I ask a question? Is this growth functions in the cotangent bundle, just I'm trying to get a sort of intuition for it. Is it sort of measuring how many fibers are used in writing a Lagrangian and its iterates under a Hamiltonian flow? So how many fibers are used to decompose the iterates of the Lagrangian under the Hamiltonian flow as an iterated cone of fibers? So you have I and L, and you try to decompose it as iterated cone in terms of the fiber.
You mean linking disk, maybe? Or so?
Let's assume you take a generator for the wrapped Fukaya category, maybe something, and you count how many of these generators you need in to write as an iterated cone the Lagrangian, and then it's no, it's not.
No. So I mean, I think you should think of it really as the growth rate of, say, the space of geodesics, for example. If you take a cotangent fiber and you look at its self-wrapped Floer homology, that's basically the based loop space. And you want to understand its filtration by length, not in this case, not by length, but by discretization of length, which says if you were to add a stop somewhere, if you were to kind of split your manifold into pieces, how many times you need to break through successive local pieces of a manifold to get your geodesic as a product of short geodesic arcs?
Benny, I understand this on the Hamiltonian side, definitely. But my question was, he has this very general definition, which is categorical.
Yeah, but that's exactly what it is, because what you want to do is you want to break an object through generators of the things you quotient by, which are like, say, for example, short linking disks of where you place stops. So you're going to break your manifold. You're going to place linking disks at the edges of the pieces. And you need to know how many times you need to factor a Floer morphism through linking disks, which means essentially how many times does your geodesic have to break through the pieces, I think.
I agree, but actually, in this particular case, just to sort of link the categorical construction to Denis' explanation, it's maybe helpful to think in terms of the categorical compactification, which comes from taking conormals of triangulation. So there you can really see sort of what's going on, rather than taking these open books. I mean, it's somehow, yeah. So I mean, I think Denis essentially said the same thing as I would have said, but if you think in terms of geodesics and you want to compute some notion of action, well, you could triangulate your manifold and then count essentially sort of +1 every time you pass through the boundary of a triangle. And if you now add a stop, which is the conormal of this triangulation, well, your cotangent fiber, whenever your geodesic passes through the boundary of the triangle, your cotangent fiber is going to hit the stop, which means that you have to pay a linking disk to cross the stop. And when you pay this linking disk, you increase the filtration by 1.
But
I don't know if this helps at all.
It does help, but okay.
But I have a much more naive question, Laurent. Could you go back to the previous slide where you talk about spherical twists?
Sure. Yes.
There's a capital G. What is G?
There's a capital G.
In the theorem. Is that an adjoint?
Oh,
On the right-hand side.
smooth categorical compactification if the image G is Q. So sorry, G is Q. It's just a typo. Sorry.
Wait, what? Oh, wait.
Sorry.
I thought C. Cur F is.
So sorry, G is F. So sorry. I mean, yeah. So G is the image of the spherical functor. So sorry, no. G is the spherical functor F. Yeah.
Or F is I.
So for instance, you could consider your spherical functor to be the Orlov functor associated to a stop, and then the image of G would be the image of this Orlov functor, which is the place of linking disks.
Okay, thank you.
Yeah. So sorry for the typo. Sorry, Octave. Did I don't know if what I said made any sense or helped at all.
That definitely it helped.
Okay.
And what Denis said,
Yeah.
I mean, it might be a relation to what I was saying, but it's different. Yeah. All right.
I see. Yeah.
And by the way, Laurent, your reformulation using triangulations is nice because you can categorically talk about, right, like taking a category of local systems on X, triangulating X, and that inducing a filtration on the category of local systems. And that involves no smooth geometry. So that is an example of a category where you don't need any, smooth structure to talk about it.
I see. Okay.
That's one advantage of your description over the usual geodesic one.
I see. Okay. So let's move on to talking about some applications of this. Oops. There we go. So let's consider what's called homological mirror symmetry for pairs. So on one side, we have a Weinstein pair, which is to say we have a Weinstein manifold and we have a stop in the ideal boundary. And this pair is mirrored to an algebraic pair, which consists of an open algebraic variety and a divisor such that the union of the variety and the divisor is a smooth and proper algebraic variety. And saying that they satisfy homological mirror symmetry for pairs means that you have essentially equivalence of categories as in equation 15. Okay, so let's pick a pair of objects K and L in the Fukaya category of X. And let's let F sub K and F sub L be mirror coherent sheaves in DB co of U. And let's pick extensions F bar and F bar sub K and F bar sub L. So this by extension, yeah, and there's a typo, it should be in DB co of Y. Okay. So the theorem says that if you have a homological mirror symmetry for pairs, then you can compute growth functions of Lagrangians in terms of the growth functions of the mirror sheaves and vice versa. And similarly, you can compute the growth function of symplectic cohomology in terms of some quantity in the mirror, which is purely defined in terms of algebraic geometry. And the proof essentially is that, well, these growth functions are purely categorical. We have equivalences of categories, and so they should be the same. But I actually do want to emphasize that in these proofs, and actually also in the previous computations, we've really made use of the fact that we have the freedom to change our stops. So as I mentioned at the beginning of the talk, if you pick two different stops, which are both kind of categorical compactifications of the Weinstein manifold, then they give you the same growth functions because they differ by zigzags. And it's very convenient in practice when computing these things to be able to pick a nice stop. So we really do take advantage of this. Okay, so one thing that's one thing to keep in mind is that, of course, we've taken one quantity in symplectic geometry, which is often difficult to compute, namely the Hamiltonian growth function, and turned it into some mirror quantity, which might also be difficult to compute. It's not clear that we've made much progress. In practice, I would say that the quantity on the algebraic geometric side involving Ext, it's usually much easier to say something about it, especially upper bounds, which are known from things like asymptotic Riemann rock. But there are some cases where we can actually say a lot, and you can more or less entirely compute the growth function on the algebraic geometric side. So let me come to this example. So this is homological mirror symmetry for the projective plane in the binodal cubic. And as far as I understand, this is a standard example in the field. So we take Y to be CP2, and we let D to be the union of a line and a conic in CP2, and we let U be the complement of D inside CP2. And mirror symmetry for this example has been studied by many mathematicians and physicists. And homological mirror symmetry for pairs is known. My understanding is that this is due to Paskarev and Hakim-Keating. And there's a Weinstein mirror, which is given by the set UV, such that UV is not equal to 1. And this is a Weinstein manifold whose skeleton is the Whitney immersion. And in this case, we can actually compute everything. So if you pick a pair of Lagrangians on the Fukaya side, and you take FL and FK to be the mirror coherent sheaves, then actually the growth function of this pair of Lagrangians is the dimension of the intersection of the support of FK and FL. And the proof of this essentially seriously uses the fact that this divisor is an ample divisor. So it would immediately generalize to higher dimensions if we knew homological mirror symmetry for pairs. And I'm not entirely sure of the state of the literature at the moment, but my understanding is that this is certainly expected and may already be known. Oops. Okay, so this was a computation. So another type of application one can consider is to studying entropy. So entropy is something which has many different meanings, and I want to focus on two such meanings. First of all, there's a notion of categorical entropy, and this is due to Dimitrov, Haydn, Kontsevich, Katsarkov. So the starting point is that you fix a smooth and proper category B, and let's also assume it's idempotent, complete, and pre-triangulated. And you fix your favorite endofunctor. And now the entropy of this endofunctor is essentially the growth of the dimension of Ext as you iterate applying the this. Okay, sorry, this is ridiculous. There are two typos in this slide. Okay, well, okay, so F is S and G is any split generator. Yeah, so you look at the growth of these X groups as you iterate applying your endofunctor for any split generator. And this is well defined. It doesn't depend on the choice of split generator. And it's called the entropy of the endofunctor. And there's also a notion of slow entropy, where you essentially look at the polynomial growth of these X groups rather than the exponential growth. These categorical notions of entropy are categorical generalizations of, or abstract generalizations of more geometric notions. So there's a geometric notion where you fix a diffeomorphism, and you look at the growth of the volume of any submanifold under iterating this diffeomorphism. And this agrees with something which is called the topological entropy of the diffeomorphism, and you can similarly consider polynomial versions where you look at the volume growth of submanifolds, but you divide by log n instead of dividing by n. In any case, some of the definitions are not so important. what I want to mention, oh, sorry, I seem to be getting something in the chat. Sorry, I should answer this. Maybe so by gamma k. Okay, so to answer the question, no, we don't need k in algebraic generators. It's only a lower bound. Yeah, so the point I was going to come to is that the growth of this function gamma k sub L gives lower bounds on these various notions of entropy. And these lower bounds use work of various other authors, including Paul Schlenk, Alves Mayweiss, Silvan, and others. Okay, I guess I won't say anything more about this for now.
Can I ask another naive question from a few slides back?
Of course.
You said that the growth was the dimension of the support of F sub k intersect F sub L or something?
Yes, I think I said that. Yeah.
I'm confused by that because the right-hand side looks constant, like dimension is constant.
Yeah. Oh, sorry. What did I write?
It was supposed to be the growth rate, I think, instead of.
So sorry. I meant the
oh, it's the exponent. Okay, great. Okay, great.
No.
Okay.
Yeah. That's sorry. I meant to divide by login.
Okay, beautiful. Thank you.
Yeah, but thanks for Okay. Okay. So I want to talk about some questions that sort of arise out of this. Yeah. So the first thing I'd like to mention is that I've only really focused so far on two types of examples. So we talked about coherent sheaves associated to open algebraic varieties, and we talked about Weinstein manifolds. But you can work with other categorical compactifications, and these invariants still make sense. So first, for instance, you could consider, instead of Fukaya categories, you could consider microlocal sheaves. This is going to be essentially the same thing as working with Fukaya categories by work of Ganato Pardicende, but sometimes maybe easier to manipulate. There are other sort of categorical compactifications which arise in nature, which would give, which somehow it might be worth considering from the perspective of these growth functions. So one source of categorical compactifications is resolutions of singularities. So if you take a singular algebraic variety, then in some cases, a resolution of singularities will give you a smooth categorical compactification of the dB-co of the variety Y. But unfortunately, we don't have any good computations in this setting. Another thing you can consider is categorical compactifications of Liouville sectors, or equivalently of pairs, or of a Liouville manifold plus a certain stop, which wouldn't have to be a compactifying stop. So for instance, you could consider a knot in the 3-sphere and then take its conormal. Well, this gives you, the Rapp-Fukaya category of T star S3 stopped at the conormal of this knot is a perfectly reasonable, smooth infinity category, which has no reason to be proper. And then you can compactify it by adding some more stops. And so then you can ask, what does the growth rate of, for instance, a cotangent fiber know about L? And is this related to other knot invariants? And I don't really know. However, I want to emphasize that when trying to develop a theory for Liouville pairs or for Liouville sectors, one actually runs into some geometric questions, which is that if you remember from the early slides, I was focusing on these compactifications coming from open book decompositions of the ideal boundary of the Liouville manifold. And we have this wonderful theorem of Giroux, which tells us that these always exist. So you can, if you have a Liouville manifold, you can always find a smooth categorical compactification by fixing an open book on the ideal boundary and taking your compactifying stop to be the one given by a page of this open book. Unfortunately, if you take a Liouville sector, you can't do this. There's no such theorem which applies. And so it's actually not obvious if you have a Liouville sector that it admits a compactifying stop. It seems sort of inconceivable that this would not be true, but it's sort of, to us at least, it was not clear how to construct such a thing. For cotension bundles, the situation is a bit better because we can use these conormals, and Ganato-Pride and Schende showed that if you have a mostly Legendre stop, you can actually embed it into the conormal of a Whitney triangulation, which means that you can somehow still construct a compactification using this. But in general, it would be very nice if one could run the same sort of theory on Liouville sectors, not just on Liouville manifolds. Okay. The next set of questions is about integrality. So again, let's take X to be a Weinstein manifold and fix a pair of Lagrangian submanifolds, which are symmetrical in infinity. And one can ask some pretty naive questions, which we have essentially no idea how to answer. So one question is, suppose that the growth of gamma k comma L is faster than polynomial. Does this imply that it's actually exponential? And we don't know. And similarly, you can ask, okay, suppose now that you do know that the growth is polynomial. Does that mean that it's sort of actually polynomial and not sort of, does that mean that that log of gamma k sub L divided by log n is an integer? So it's not something like x to the power of 1/2. And we don't know how to answer this question either. So what is some evidence? Well, we have extremely slim evidence. I mean, it's not really fair to even call this evidence. Concerning the first point, which is this question of whether the growth is either polynomial or exponential, I should mention that if you consider the case of cotension bundles, well, there's a somewhat related dichotomy in rational homotopy theory, which essentially says that the growth of the dimension of the base loop space is a function of n. Sorry, there's a typo. It should be I lesser than or equal to n. The growth of the dimension of the base loop space is either polynomial or exponential. And so if you use this fact, then you can translate this into symplectic terms using the work of Ampantadoro-Schwarz and Abu Zaid. So this sort of suggests that maybe something like this is true, but I want to emphasize this is extremely sort of flimsy evidence. So there are many cases which are not covered by this attempt. Concerning the integrality question, so this is question number 2, the only piece of evidence we have is that in the case where X is mirrored to the complement of an n-canonical divisor, then this follows from the computation that I mentioned in the previous slide. It also seems to some degree like, at least for examples which have algebraic mirrors, you would sort of expect this growth to be something integral. But this is not really extremely flimsy evidence. You can also ask similar questions about entropy, polynomial entropy, entropy of various spherical twists, which I mentioned earlier. These questions might actually be more natural. I'm not sure, but in any case, we don't know answers to any of them. Okay, thank you very much. I'll stop here. Thanks a lot for listening.
Thank you very much. So, of course, if there are more questions, please don't hesitate to ask. So there are some. Okay.
So I have some elementary questions that has nothing to do with symplectic stuff. So regarding your dichotomy of exponential versus polynomial, what does the growth rate of, say, chains in the base loop space, does that have anything to do with the growth rate of the fundamental group?
I think that typically when one considers the growth rate of chains on the base loop space, you assume that the fundamental group is trivial. And in some sense, my understanding is that people like to view the homology of the base loop space as a sort of analog of the fundamental group when the fundamental group is 0. When you have fundamental group, you can also consider the growth of the fundamental group, which sort of will also give you, there's often a similar sort of dichotomy in the case.
I see. So then for your question 1 of integrality, I mean, is it possible that you can take one of these manifolds whose pi1 is sub-exponential growth?
Yeah, if you have such a manifold, but I don't think that you can, I'm not sure they exist.
Oh, really?
As far as I know, it's at least not known.
Oh, okay, gotcha. My fault.
Oh, that's fine.
Is it possible in this setting to define something like a barcode? So kind of, usually in filtered homology, yes, so these days we know that if there exists barcodes, yeah, so coming from persistence models, from which you can read, of course, the growth function, but actually more than that. And,
yeah. So somehow the filtration we get is only meaningful up to the scaling equivalence. So this barcode would not be well defined unless you're willing to mod out by this scaling equivalence. It's really sort of like an asymptotic invariant somehow. So you certainly could, I mean, if I could just return to the, let me see. So the construction was basically you fix your categorical compactification and you fix some split generators in the kernel and you get a filtered category. So of course, once you have this filtered category, you can talk about barcodes. The problem is that you've made some choices along the way. And if you were to make different choices, the filtrations would change. However, what we're showing essentially is that this change is only introducing a scaling equivalence, which means that at least sort of if you only look at the large scale kind of growth of these complexes, they're still related. But I'm not sure what sort of information you could will be preserved under the scaling equivalence, other than the growth.
Scaling equivalence probably should say that you are kind of at some finite distance in bottleneck distance on barcodes, right? Because you have infinite barcodes, you can probably look at the asymptotics of finite bars.
I see. Okay.
Yeah, I don't know.
I see, but yeah.
So maybe very related to what Leonid asked, it's kind of same. So there is this notion of triangulated persistence category,
yes, yes.
which I kind of have some sympathy for. And I was just curious if these things are that. So in other words, of course, this will depend on your choices. So, and maybe on more. I mean, not only maybe on the generators of the kernel, but maybe more data will be fixed. But I'm curious if these examples are in fact examples of that.
Yes.
The definition for that is very easy. So you have to have a filtration for the morphism spaces, which you do.
Yes, yes.
And if you look to filtration zero morphisms, which okay, are the simplest in a way, they should match together in a triangulated category. And that's basically it. So in a way, I think it's easy to check if this is true or not. Maybe it's not, but that is, you have to be able to take cones over all morphisms of weight or of filtration zero, and with functoriality properties as. So it's a question.
Yeah, I guess at the start of I mean, when we started working on this, we were sort of wondering whether your work with Biran and Zhang would be sort of either overlapping or related, but we never really sort of found an answer, and we eventually just decided to move in a somewhat different direction. But I was meaning to sort of return to this, but unfortunately I haven't done so yet. Yeah,
but you know, it's great to see. I mean, it's definitely different direction, but it could be that indeed the structures have some overlap. So that's just, you know, to be looked at. Right. So maybe other questions. I don't see. Other things around here. If not, we can thank Laurent for a beautiful talk.